Hey everyone, this is Dr. Walker. Let's look at a couple of examples from video 101C on free fall acceleration. In this your turn, it says, Planet X has free fall acceleration 8 meters per second squared at the surface. Planet Y has twice the mass and twice the radius of Planet X. What is the free fall acceleration on Planet Y? Let's take a look at the equation that we just learned to find free fall acceleration. G equals gm over r squared. M is the mass of your planet, and r is the distance from the center of that planet to where the object is. In this case, the object is going to be at the surface since we're trying to find a free fall acceleration at the surface. So in this case, the little r is just going to be the radius of the planet. So go ahead and try it on your own. Pause the video and see what you come up with. All we need to do is see what happens when we change m and r. I'll do it in red. The little g equals big G times twice the mass, so 2m, divided by 2r. Make sure to square the 2 and the r. When we do this, we get g times 2m over 4r squared. So we get 1/2 gm over r squared. If we compare our g, our lowercase g, to the original one, we can see that we have half of the acceleration. So instead of having 8 meters per second squared at the surface, we're going to have 4 meters per second squared at the surface. Let's take a look at another example. The radius of the Earth is about 6,370 kilometers, while that of Mars is about 3,390 kilometers. Mars has a mass of 0.107 of that of Earth. What is the acceleration due to gravity on Mars? We're trying to find g. We can use the same equation that we just used. Little g equals big G m over r squared. In this case, we're not given the mass of Mars, but we are given that it is 0.107 of that of Earth. If we're trying to find g on Mars, let's use little subscripts here. So g on Mars is big G, mass of Mars, and radius of Mars, right? Remember, the r is going to be the radius of the planet if we're assuming that we're on the surface. So since we don't know the mass of Mars, what we can do is we can plug in 0.107 times the mass of Earth, because that's what the mass of Mars is, divided by the radius of Mars squared. Now we just need to get an expression for the mass of Earth. Well, let's do that on the side. If we use the same equation again for g on Earth equals big G, mass of Earth, divided by radius of Earth squared. So from this, we can get an expression for the mass of Earth. The mass of Earth is going to equal g on Earth times the radius of Earth squared over big G. Now we just need to plug in this expression for g, for mass of Earth that we just found, into our other equation here. Let's see what happens. We get that the free fall acceleration on Mars is equal to g times 0.107 times all of this. G on Earth, radius of Earth squared, over g, and all of this is divided by radius of Mars squared. We see that the g's cancel out, the big G's, and now we can plug in all of our known information to find g on Mars. We're going to have 0.107, g on Earth is 9.8 meters per second squared, radius of Earth squared, we're going to plug in this number right here, 6,370 times 10 to the 3 meters, right, because it's kilometers. Make sure to square that, divided by the radius of Mars, 3390 times 10 to the third squared. And we will get approximately 3.7 meters per second squared. So that is the free fall acceleration on Mars. This was part A. Let's look at part B. If an object weighs 200 newtons on Earth, what would it weigh on Mars? So we know that this weight is also mg. This gravitational force is the weight. So Fg equals mg. We know that the weight on Earth is 200 newtons. This allows us to solve for the mass of your object. So the mass of the object is going to be 200 divided by 9.8, because all of this is happening on Earth. That gives us about 20.41 kilograms. Now that we know the mass of the object, and we know that the mass doesn't change, if the object is on Earth or Mars, it will still have the same mass. So now we can look at the weight on Mars. We're going to have Fg on Mars equals the mass times g on Mars, times the 3.7 instead of the 9.8. So multiply 20.41 times 3.7, and we will get approximately 75 newtons for the weight on Mars. As we expect, an object will weigh less on Mars than on Earth, but it will still have the same mass in both places.